Well, welcome back, folks. Looks like we can get started. And congratulations, we've made it through midterm week. The second exam, the portion where it says course score, that's now taking into account average of your exam one, exam two score, and all the homework that was due up to date of that exam. So your course score is your midterm grade that's printed on there. As far as the average statistics or basic summary statistics goes on this exam, the average grade came out to 84.3%. And a maximum grade of 100% was obtained by 3 students. I think that's pretty hard on this exam because the concept questions are tricky. There's lots of little details in linear algebra. So congratulations, folks, we're nearly there. If you'd like to take a look into the solutions, I have it posted here on this document. And same for exam one. We'll pretty much just repeat the same thing for the third exam and for the final exam as well. If you came back to the Canvas page after finals week is over, you can find the solutions for the final exam posted in the same kind of way as well. Well, that's my major announcements to start us out. We're now on week 9 over the 50% mark. Any questions to start us out today so far? Okay, well, there's lots on week 9, but that's because we got most of the way through section 3.2. Section 3.3, we're not going to cover in entirety, so this is going to be a pretty short stop here in 3.3. The homework assignment is pretty short as well to reflect that. And section 4.1, we're turning into chapter 4 next, is a really long section, so we'll probably be working on this pretty much through Thursday, I would believe. We'll see where we end up after today's class. This material suddenly becomes a little bit more abstract, but at its heart, what chapter 4.1 is doing is the same thing as what chapter 1 was doing, except that the vector spaces we're studying aren't necessarily Rn. They could be more abstract objects. So that's where we are so far. We left off on example 4 looking into properties of determinants. Essentially, we're nearly done with chapter 3 already. And here's where we left off on. This was a while ago. This was right before getting into the exam. So a week away from today, we looked into 4 major theorems to help support taking determinants. But maybe even more important than all that, we found from the very start of this section that if you're going to take a determinant and you want to do it as efficiently as possible with by-hand computations, then theorem 3 is the major tool that we use. Parts B and C, while sometimes useful, aren't used as often. And if you look through the notes, I haven't really used them too much, except for example 1 where it's kind of forced in. But part A is major. It tells us that we can take a determinant by combining row operations inside here where the determinant function is being indicated. And, well, that's the different thing we did hit on this one right here. And it makes no change in the actual determinant itself. We get to write identically equal to on the left and the right. The equal signs are weird here because we made a big deal out of this in chapter 1, that when we change a matrix, we are using the row equivalence operator, that these matrices aren't exactly equal. But the reason we're using equality right here, even though we used row operations to go from one step to the other, is because those vertical bars are giving you a real number. The result is just some output, some number itself. We're saying down here that number is equal, even though we used a row operation. So these aren't equal to matrices any longer. It's just taking a matrix as the input of the function. Well, that was our big theorem that we used last Thursday. We found we could take this 4x4 determinant in a really rapid way. We didn't actually have to do 3 2x2 determinants, because if we did a fast row operation to eliminate that 2 right there, the cofactor expansion down column 4 just turned it into 1 3x3. We didn't solve for that either. We also eliminated this -6 here, and it turned a 4x4 determinant into doing 1 2x2 determinant. So if you work really cleverly, finding the most nice way to put lots of zeros in your matrix, this is what determinants by hand typically look like. It's not as bad as you might think, and if you're still doing the homework in section 3.1, you're welcome to take those kinds of shortcuts as well. So other things we worked on were finally looking into this list of theorems, we derived one from scratch just to see how these properties work together. Further properties of the determinant tell us you can transpose a matrix and it doesn't change the determinant function. There's a multiplicative property. Now, this is pretty major. And there's a kind of power property as well. The A power -1 is a matrix inverse. And this is just the reciprocal. So you could say it as a true exponent, power -1 here. Combining this theorem and this theorem tells you no matter what the power n is, as long as it's an integer, you get this kind of property, which is a consequence of the multiplicative property and the inverse property all at the same time. The last part of the notes is just working with these last four theorems all together. Any questions so far, folks, with the quick tour of what we did last week? Okay, there'll be problems using these theorems on the exam, but really they're not too bad. Here's about how they go. You'll get problems that looks like you're doing a whole bunch of computations, but it's really just a tour of the theorems that we saw above. And this one we copied and pasted from the very top of the notes down because it's a very useful formula. First thing we'd want to do is compute the determinant of A to get this started. So this is just a normal computation. Determinant A. Definitely you want to save some time. You could spend all day on a particular single problem on a matrix doing its determinant. We don't take advantage of the properties. So let's maybe eliminate these two entries right here to get it started. Copy in row 1, 1, 5, -4. Add row 1 to row 2, replacing it, and we'll get 0, 1, 1. Double row 1, add it to row 3, replacing that one, and we'll get 0, 2, -1. Let me double check that. -8 plus 7, so a -1. At this stage, you can go even further and eliminate this 2 right here, but it's kind of up to how you'd like to calculate it. Sometimes getting echelon form, like we mentioned, is more trouble than it's worth. You'll see that in the homework. It's okay to just kind of settle for this because the computation's really fast right as it stands. Cofactor expansion down column 1 would give you a 1 times the size down submatrix, 1, 2, 1, -1. And this is really fast to calculate. So we would just get, let's drop the 1 right here and get -1 minus 2 for -3. And it's done right at that step. If you did the row operation, you would have had a triangular matrix. And I think it's kind of equal in how fast it would take. But sometimes it's not easy to get that echelon form. So I encourage you, if it looks like the numbers are just not friendly, just stop at this kind of point and work it through. So that was our first bona fide determinant of the day. Next one is just choosing properties. Determinant of A squared. You could either use theorem 6 or think in terms of this unnamed theorem down below. It's kind of nice in a way. The power 2 just commutes on the outside. Determinant A squared is the determinant of A. It doesn't need an input. It's a bona fide function. Is the determinant of A squared. So we just bring in the -3 we just calculated, square it, and we're on our way. Some of these formulas are going to appear on the exam, but it's a really good idea to memorize them as much as possible. That way the cognitive load on everything floating around your head, the exam 3 isn't too severe. Best way to kind of memorize these formulas, get them into muscle memory, is just write them down every time you use them. We've probably made that comment several times now. And we'll do that some more for the next ones. For determinant A inverse, thinking in terms of we'll eventually have to do this on exam, I would write down on homework, determinant of A inverse is 1 over determinant of A. This automatically is like studying for the exam at this point, getting that formula in your head. 1 over the determinant of A is just 1 over -3, so it's -1/3. And that's 2 down. They go pretty fast. Any questions at the moment? Okay. Honestly, chapter 3 is kind of a nice chapter. I think chapter 1 ended really abstract with the linear transformations, all the theorems rolled into one, and then we had the invertible matrix theorem in chapter 2. So this is kind of nice, just computational type of problems we're doing at the moment. Determinant of A transpose, well, that's the purpose of this theorem up here. It tells us you don't have to work too hard. That's just the determinant of A. which we've computed already, and it's -3, just substituting back that information. And out of all of these, I feel like this one is the trickiest, determinant of 2 times A. This is the one that gets missed the most in an exam setting. To do the determinant of that one, you do need to know the size of the matrix you're working on. If this was 2 by 2, the formula goes different. If it's 5 by 5, it's different again. That's all based off the size of the matrix. So first thing you want to think about is it's a 3 by 3 matrix on this problem. So that means determinant of 2 times A. Well, this is going to multiply 2 into every single row of the matrix A. So all the way back here on the top, that means this formula happens 3 different times. The value 2 gets multiplied into row 1, gets multiplied into row 2, gets multiplied into row 3. And so we would have 2 to the power 3, think in terms of this formula. Or just as a new theorem, this is a great way to just paraphrase all that. So we get all together, determinant of 2 times A is 2 to the power of 3, multiplied by determinant A. So this becomes 8 times -3, for a -24 altogether. That's a pretty quick tour through just about everything here that we saw, all these properties. Any questions at the moment, calculating any of those? Okay, it goes so fast, I felt like when I wrote these notes, we ought to just do it again. So for a slightly different scenario, let's look into 2 matrices, work through these problems again just to see how it goes. Here's the new run through. Same set of theorems, just here for easy reference. Problem goes a little bit different because everything is kind of unknown. I don't know the original matrix A or B, except it is of size 3 by 3, so we'll have to be careful with that size. We already know that the determinant of A is 4, determinant of B is 5, so we'll use that information as it comes up. And we're just doing 4 computations like before. First one, determinant of A times B is the multiplicative formula. Determinant of AB is just the determinant of A multiplying the determinant of B. We made a big deal out of this last time, but the determinant function is really pretty bizarre having that property and all of the other weird properties it has on these notes. It's a really rich function with lots you could talk about. You could turn this into pretty much the rest of the semester talking about the determinant function and all of its features. So we're just paring it down to these last concepts and then Cramer's rule next. Determinant of A came out as 4, so we'll just substitute that in. Determinant of B came out as a 5. At this stage, we're basically done. The product of the matrices determinant is 20. So that's kind of nice in a way. Recall that these properties seem like they're going fast in a certain sense, but you have to imagine this is an exam situation. If you're doing this problem in an exam situation, this is one of those times where you could accidentally spend like 10 minutes or 15 minutes doing this problem because some people might think you need to calculate A squared to get this value. You have to compute the A inverse and then calculate the determinant of that. That's a lot of time you might be wasting. The transpose might not be as dangerous, but this one could be just as equally damaging. If you try to do all these by scratch, by finding the values of every one of these matrices, you could be doing this problem all day. So at every time you're doing linear algebra, it seems like there's always a hint on these exams. But if this was an exam 3 problem, there's not a lot of space on this problem. That's the hint. You're not really meant to show a lot of computation. You're meant to find the right theorem to pair it with to move through it pretty rapidly. Less danger on this one because we can't calculate A times B. We don't know the original matrices. The next one is determinant 3 times A. This is where we use, oh, that theorem we cite isn't there, but we use the property that 3 times A means we're multiplying all rows of A by 3. So it'll be 3 to the power of the number of rows. Probably should have changed this to 2 or 4 or something just for variation, but a little bit emphasis on the notes is that this should always be equal to the number. Well, rows or columns, it has to be the same amount of rows or columns for the determinant to be defined. I should say columns because we are highlighting the column, equal to the number of columns. Then multiply it by determinant of A. So that would be 27 multiplied by determinant of A is 4. And I wasn't prepared for this kind of math today, so that's 80, 28. That comes out to 108. Guess that's a good reminder as well. Don't forget to bring a calculator on exam 3 for just in case the numbers get large. The power's 4, for example. Next one is determinant 2 times AB. Another strategy that you can always take on an exam is anything you do on the exam, you can always use again on another problem in the exam. For example, if you already done determinant of A times B, even if you did it, say, as problem 1, and then this came up as some other part of the exam, that'd be kind of weird. But if that ever happened, you can just cite what we've already calculated. So using the property that we did just above, we could rewrite this as 2 to the power 3 times determinant of AB. Then we don't have to work too hard on this because we've already calculated determinant of AB. So we'll just drop in that value. So this is 8 times 20. And we get 160 out of that. So even though this was kind of a simple context, the concept is anything you've calculated is fair game. You can just directly use it up again. Even without explanation, I would have known that this had already come up in the exam. You just made a huge substitution. Last one is determinant A inverse times B. This one's kind of a fun formula because we're using this property together with this property all at once. But really, instead of using multiple properties, you can just combine them. And the short of this is if A inverse comes up, this is really just determinant of B. Divided by determinant of A. And that's the paraphrase of using now just multiple properties all in one shot. Determinant of B is the 5 and A is 4. So we substitute in those same values from before. And our work is done right at that step. So they're pretty cool properties. We'll practice some of these in the exam, in the homework assignment as well. They'll come up on an exam in one form or another. Any questions at all, just using them directly like this? Okay, this one is usually kind of a faster exam problem if it came up in exam 3. But again, watch out for this one because this is one where it gets dangerous. You can really lose your way if you did calculate any of these from scratch. The idea is you never had to. You can just use the properties. And chapter 3 is kind of weird. Our prior chapters in the book sometimes were pretty long. The sections were long themselves, but this is a pretty short section as well. It's pretty much done. I threw in just one additional problem for the sake of seeing other interesting things we can do with these properties. So this will be our last example of section 3.4. Skew symmetric matrices tend to have loads of applications in linear algebra as well as other areas, physics and engineering. The short definition is that a matrix is skew symmetric if its transpose is equal to negative A. These matrices automatically have a lot of interesting properties. You could deduce from just this definition, skew symmetric matrices have to have a main diagonal that's identically equal to 0. That's because when you transpose a matrix, the main diagonal doesn't actually change any longer. This is supposed to be square, so your main diagonal didn't change. And if it's equal to negative A, the only way an element is equal to an opposite of itself is if that element was 0. So skew symmetric matrices have a main diagonal that's 0, and lots of other bizarre properties. So here's a bizarre property we're going to look into. If we have a square skew symmetric matrix and n is odd, show that the columns of A are linearly dependent. That's a bold statement. Skew symmetric, along with the odd size when it's n by n, automatically implies linear dependence. Makes you wonder what happens when it's even. There's something specific going on about odd. And another reason to throw out in this problem is it's just another call out to the invertible matrix theorem that we'll use to get through this problem. So linear dependence, that's talking about, let's see here, part E in the vertible matrix theorem, vertible matrix theorem. invertible matrix theorem. For some reason I thought I said that wrong. That's just part E. So if we can combine that with something else here, so this is all supposed to be false for this matrix, our work will be done. And this is one of those weird problems where it's hard to know where to start. So we'll just start with assume the matrix is skew symmetric. So we have just that. That's essentially all we know. A transpose is negative A. So I haven't done much. This is not really progress other than just writing down the property. Other things you might think of is, well, this is a section on determinants. And in the invertible matrix theorem, the determinant does come up. So if we have an equation, you can always do the same thing to one side and the other, whether you're integrating it, if that would make sense in the context, or differentiating it. Determinant's just another kind of operation. So we can take the determinant of both sides of this equation. Determinant of A transpose becomes determinant of negative A. But now we have a bunch of properties we can use here. The fast one is determinant of A transpose. That's just the same as determinant of A, so we can make a substitution there. So on the left-hand side, we can immediately write in just determinant A. That negative we'd like to pull out, but we have to be careful. The property that goes with that negative sign right there is much like when we had determinant of 2 times A or 3 times A. When that negative comes out, we have to say determinant of negative A is really the scalar to the power of n, the number of columns, times determinant of A. So working that really carefully, this is probably the trickiest part about it. That negative 1 right here, the number of columns of n all combined together, this turns into negative 1 to power n times determinant A. So now we have just determinant of A on both sides of the equation, negative 1 to the power of n. We have used up just about everything we can. We've used up the fact that the matrix is skew symmetric. We use the size of the matrix right over here. We've used these two properties of determinants. The only thing we haven't used is the fact that n is odd. That turns into kind of the punchline just about. If n is odd, that would mean negative 1 to the power of n is just negative 1. So we can just substitute in here directly negative 1 itself from that information. Determinant of A equals negative determinant of A. But just like what we were saying up here when we said if you have the diagonal equal to the negative diagonal, the main diagonal is now 0. Same idea over here. If an ordinary scalar is equal to the opposite of that scalar has to be 0. But we can just take it down to its algebraic inevitability. You can add determinant of A to both sides of this equation. 2 times determinant of A is now equal to 0. Divide by 2. We have now said directly determinant of A is 0. Once determinant of A is 0, invertible matrix theorem is on the table for us. It negates part n, and so now it negates part E as well. The columns of A are now known to be linearly dependent because we had a 0 determinant, not a non-zero determinant. So at this stage, we're done. We can say, therefore, by the invertible matrix theorem, the columns of A are linearly dependent. Again, that's a pretty weird fact because it used directly that the size was odd. This is not guaranteed to be true if it's a 2x2 skew symmetric, 4x4, and so on. Something's weird about the 3x3, 5x5s, and 7x7 skew symmetric ones, and so on. But that again was just our last look at these different properties, how they go together. Invertible matrix theorem is the main idea behind this problem. Sometimes there's problems like these in the homework. Usually probably not very many. If you ever feel like you're just stuck on one of them, don't hesitate to write about it. I'll be happy to give out hints, say what to try out, those kinds of things. We did it, folks. That's the end of section 3.2. Any questions at the moment with what we've done so far? Okay, we're also nearly done with chapter 3. Chapter 3, again, the major purpose we're going to use is determinants is going to be a major tool when we go to look into chapter 5, dealing with eigenvalues and eigenvectors. We need the determinant to find specifically the eigenvalues later on. To get the eigenvectors, that was the parametric vector form skill that we've been hinting at and talking about quite a bit through the course. So we have just about everything we need, but we want to go through chapter 4, that's the order of the course after all, before getting into eigenvalues. Sometimes it feels like the course is ordered weird. Chapter 3, in a way, kind of fits in after chapter 4. But going in the order of the course, this is going to be our next topic, Cramer's rule. This section is also really short, and the homework is very short as well. This is just another way to solve a system. We have ordinary row reduction to solve a system of linear equations. We also explored in section 2.2 an alternate way to solve a system of equations when this number of equations is equal to the number of variables. So as a matrix equation, the matrix would be square. We have this, when the inverse exists for a matrix equation, ax equals b, the solution is automatically x equals a inverse times b. And we did this in the section 2.2 homework, solving a system this way. This is relevant because this is an exam 3 type of problem as well. This is a pretty typical exam 3 problem. And when we go into Cramer's rule, the idea with what's going on there is we're looking into these kinds of systems as well. And we're going to look into another way to solve this. This is going to be another exam 3 type of question. So this is what the rule looks like. For solving the matrix equation ax equals b, we now have 3 methods. Row reduction is really powerful for by-hand computation. We can use this method, just solve for x as a matrix equation. You can solve for that directly. We briefly talked about why there'd be benefits of doing it this way. And now the third way is Cramer's rule, this strange little formula here. And I think this is a good thing to talk about. There's a word of warning in that Cramer's rule is not the fastest way to solve things by hand. Even computationally, it's pretty heavy computationally to make it happen. But there's big benefits of Cramer's rule. There's some things that we shouted out here on visualizing it in a nice way, where Cramer's rule explained geometrically. But probably the bigger benefit of Cramer's rule is that it's another theoretical tool. If you have taken, you are taking, or you will take differential equations, one big method for a second order of differential equation is called variation of parameters. It's exactly Cramer's rule, just looks a little bit different because you're dealing with functions. Another great use of Cramer's rule is in anything that has to do with applications, engineering, electrical engineering. You might be modeling some kind of system. And if you're wondering how one variable is going to change based upon a parameter, this tells you the solution for one variable at a time that you can look into directly. So that's kind of the big takeaway with Cramer's rule. It's the hardest way to solve a system oftentimes, but it's a major theoretical tool, and it's really good for system modeling. That's going to be the thing that we look into down below here. There'll be a homework question just like it, where there's a parameter inside the system, and we're wondering what happens to the solution as a parameter varies. The parameter in this one was S. So that's my spiel on Cramer's rule. It's not everyone's funnest process because we have to be honest, it's not the fastest way to solve things. It looks complicated when you look at it on face value. It's actually a pretty straightforward process. On a real exam, it's only going to be with 2x2 systems, since I'm most concerned about the concept of it not getting kind of bogged down on long computations, heavy determinants. But for any kind of new rule, there's usually a lot of new notation, and this is how it goes. If we have a square matrix, this is where Cramer's rule is valid. We're interested in the vector b in Rm. That's going to be the right-hand side for the system of equations written in matrix form. And we form this new notation, AIB. What this means is we're doing a full replacement of column I in the matrix A with the vector b itself. Written out, this is what it looks like. Here is column I right in this position. We replace with the right-hand side the vector of the right-hand side on all the equations in the system, the vector B. And that's what A1B, A2B would mean. These are the components that we're going to be using in Cramer's rule. It's kind of like when we were doing determinants and A13 meant delete column 1, row 3. This time going A1 and then parenthesis B just means insert the vector B in that column and that column, where the subscript is going to say where the insertion happens. So if that's our matrix A, AX equals B is just a system of equations in matrix form. And A1B just means go to column 1, insert the vector B. Our vector B is 9, 8, so we'll go here. The rest of the matrix A, we just copy down directly, 5, 0. And that's it. That's our new notation, A1B. Again, saying it in the linear algebra sense, writing down all the notation, it's a lot of reading, a lot of things you have to stare at to see what we mean directly. But putting it down on paper, it's just another pretty fast pattern to write out. Does that make sense to folks so far on writing out that notation? Okay, likewise, A2B means go to the matrix A. In column 2, we're putting in the vector B from the right-hand side, 9, 8. Let me try getting the color coding. 9, 8 would go here. The rest of the matrix is -1, 14. And that's the meaning of A2B. So no matter how big the matrix is, we'll do a 3 by 3 matrix. A1B, A2B, A3B, if the matrix is of that size, just means doing this kind of thing. What we'll be doing with these things is just taking their determinants, and that's the idea with Cramer's rule. Turns out you can solve this not just by using a matrix inverse, but also by just taking determinants of these kind of matrices and the determinant of A itself. So that's probably the most confusing thing about Cramer's rule. Putting it together is pretty fast. It's just another pattern that we put together. Even though the homework is short, the practice you'll get in the homework will make it pretty clear how this all goes. So Cramer's rule, its proof is kind of technical in a way. I'll direct you to the reading of the book on the justification on how to prove it. There's also, again, the optional video here you could take a look to if you'd like a more geometric, intuitive view on what Cramer's rule is trying to say. But it's not too long to state. The Cramer's rule tells us if you're solving this equation here, critically your system has to be of size n by n. Then the solution to the vector x here is just given in this way. Every x component is the determinant of AIB divided by determinant of A. And that way, solving a 2 by 2 system, it's kind of fast. It's pretty competitive with ordinary row reduction. But for a 3 by 3 system, these determinants start to get a little bit more involved, and row reduction is the faster method usually, unless the matrix just has features with lots of zeros to make it faster. So to give this a shot, the major thing you'd want to do practicing Cramer's rule is just get into a methodical process. Do it the same way each and every time, and you'll never get mixed up on what goes where. First thing you'd probably want to calculate is the determinant of A itself. But that means you have to find the matrix A. You have a system of equations. This is how it's going to be written in an exam setting. From the system of equations, we want to write out the matrix A, the vector x, and the right-hand side, the vector b. So this is ax equals b, which we're indicating. The vector b is 3, 1. So that's the major portion of Cramer's rule. Matrix A, we just pull coefficients. It goes 1, 3, 2, -1. And x here just has components x1, x2. And that's this part of Cramer's rule, indicating which value they're going to solve for. So if we were doing system modeling and we're only concerned about, say, in a large system, x4, we could just investigate what happens to the solution in x4. Whereas on this problem here, if we're looking at what happens when the system, if we make a change for the vector b, this is giving you the change for all values x1 through xn. So So Cramer's rule is kind of more refined. We can look into just one variable at a time. For the sake of homework, though, we're going to look into solving the total system, so both variables, just to get a feel for how it goes. So next thing to write down is, like we mentioned, determinant of A itself. We have the matrix A, so that's pretty fast. Determinant of A is 1, 3, 2, -1. Just copying this over here to connect it with the notes. So this becomes -1 minus 6 for -7. Then just two more determinants to get through. That's going to be the numerator part. The solution for x1 is now immediately found to be determinant of a1b. So that means it's going to be a1b means replace column 1 of the matrix A with the right-hand side B. So it becomes a 3, 1. The rest of the matrix A is 2, -1. Our denominator we pre-calculated is -7. So it just drops in down below into that position. So that's Cramer's rule for x1 itself. We need to do it one more time and also finish off this one. But does that make sense to folks, putting it all together? Okay, let's finish this one off. So product of the main diagonal would be -3. My subproduct of the off diagonal is -2. Divide by -7, and we get altogether 5/7. And that's done now. X1 is done. I mean, it's kind of nice in a way if you feel like row reduction is not the funnest thing in the world. This is a way to get out of row reduction. Just use determinants instead. X2 is going to be really the same kind of pattern. And I noticed I didn't copy the formula down here. Let me fix this. I need a determinant A down below. Let's just smack that with the highlighter to make that apparent. So now for x2, it's going to be determinant a2b, divide by a determinant of A. Just like before, we're taking the column B. This time, the subscript 2 tells us it goes into column 2. So 3, 1 is now in this position. The rest of the matrix A we get from up here, 1, 3. The denominator we already calculated is -7. So that means this one's about done. X2 is going to be 1 minus 9, divide by -7. So it's an 8/7. We got it, folks. So for this original system, solution set is unique solution 5/7 and 8/7. We know it's got to be a unique solution because the moment we got the determinant is not 0, it shouldn't be 0 for using Cramer's rule, but also means there is going to be a unique solution if the inverse exists. Well, any questions at all solving this one? Okay, again, it's just a weird new number pattern in a certain sense. It's kind of like row reduction being a new numerical way to do things to solve systems. Determinants has its own rules and new patterns numerically. And this is a big application to determinants. Cramer's rule goes together in this kind of way. It's pretty fast for a 2x2 system. And for a 3x3 system, this is where it starts to get a little bit more gnarly, but we'll practice it just for the sake of, I think there's one in the homework, and it's a great way to really practice Cramer's rule itself. So if the system is this large, we want to solve AX equals B like we mentioned before. But the critical things that we're going to be operating with are the matrix A itself. That's just the matrix of the coefficients on the left-hand side. So 2, 4, -2, 1, 5, -1, -3, 1, 4. Let me know if my numbers go sideways on this because this is now a lot of computations. The column vector B in Cramer's rule is 0, 8, 2. I wish I put more zeros in there, but this is what it is. So we'll work with what we've got. First step I would take in Cramer's rule, after writing down what the matrix A is, the column vector B is just crank out the determinant of A right away. Because the system is of size 3x3, there's going to be 4 determinants altogether. All four of them are of size 3 by 3, so this is a lot of computation. That means we're going to want to use tricks from the trade in section 3.2 to compute these determinants as fast as possible, or else this is a humongous problem. So to start this off, doing determinant of A, we wouldn't want to do it in the form that we see back here on the red dot. Let's start to eliminate some columns. And it's really kind of up to you on what you'd want to eliminate. I'd probably go for the 4, -2 on this one. The numbers just seem convenient this time. So I'm going to leave row 1 as is, 2, 1, -3. Multiply it by -2, adding to row 2 is going to give us 0, 3, 7. Next, we can take row 1, add to row 3, replacing it, and that will give us 0, 0, 1. Whenever you get a matrix like this, it's always good to kind of pause and reflect how nice this one is. This one is upper triangular. We looked into a lot of properties in section 3.2, but one of the major properties that you should take advantage of that will come up on exam 3 is the determinant of an upper triangular matrix is just the product of the main diagonal. So once we get here, we don't have to work too hard. It's 2 times 3 times 1. So determinant of A is just 6, and that's a big help for us. Next, we need to solve for x1, x2, x3. Instead of writing it out that x1 is determinant A1b over determinant of A, I'm just going to focus on the numerator so we don't have too much stuff we're copying along each stage. So in the next step, it'll just be determinant A1b. So it's a new 3 by 3 determinant. Column vector B goes into column 1. So 0, 8, 2 goes here. The rest of the matrix copies in as we saw it right above. 1, 3, 0, -3, 7, 1. Now we have to make a judgment call, decide where is it going to be easiest to get the most amount of zeros. Column 1, column 2 are good candidates. But if I'm going to eliminate that 8, I might make the numbers kind of large. I think this 3 would be a little bit easier to eliminate. Let's get zeros on column 2. But really, it's up to you. There's loads of ways to do these kind of problems. I'll go with eliminating that 3 by the red dot. So this will be, I'll copy in row 1 as is, 0, 1, -3. Row 3 looks just fine, 2, 0, 1. To eliminate that 3, I'm going to multiply row 1 by -3, adding it to row 2. That'll give us 0, 8, 0. Numbers got large, even though I was trying to control that. So that's 9 plus 7 for a, let me try that out again. 9 plus 7 for a 16. At this stage, going down column 1 looks like a good choice. The sign chart for this is going to be positive, negative, positive, negative. Critical thing is we have to switch the sign on this one with that cofactor expansion down column 1. So this will now be -1. That negative came from this sign chart to the right, multiplied by the reduced determinant, 8, 2, 16, 1. Now we're just about there. This determinant turns into the negative of 8 minus 32. So that's going to be the negative of -16 for a positive 16. This is a lot of arithmetic on a Tuesday. Doing this as a night class can be tough. When you get tired, arithmetic is usually the first. But any questions at the moment? Okay, well, we already have.
Right. 8 minus 32, wouldn't that just be -24?
It would. Thanks for catching that. If I take 8 plus 16, I get to 24. So that'd be -24. Again, the arithmetic, don't even think I'm that tired, but still, I think that step was just a bit too much for me. Thanks for catching that one. So then this turns into a positive 24 altogether. Other questions at the moment? Okay, let's It's always rough to get the arithmetic right there taking you down. If this was a real exam question, I'm usually going to be probably a little bit more forgiving on the arithmetic because it does get a 10 starting in chapter 3. So if you got the right idea down, the right form, I probably wouldn't even take off a point on this kind of work right here, maybe a half a point at worst. Well, we could start writing down what x1 is, or we could write down what x1, x2, x3 is at the very, very end. It's kind of up to you. I think if we're calculating these things, we might as well just go off to the next one and get them all out of the way. So next one is determinant A2B. We're halfway done with all the determinants, so that's the good news on this one. Determinant of A2B first starts out looking like this. 082 goes into column 2. At this point, it's kind of nice because you're really seeing the pattern in Cramer's rule a little bit better if it's a 3 by 3. Copy in the remaining columns from the original determinant, 2, 0, 0, negative 3, 7, 1. And this is a fast determinant. We already have zeros lined up on column 1. So the fastest thing to do, I would say, is just a cofactor expansion down column 2. Or excuse me, down column 1. So this will give us a 2 times reduced determinant, 8271. Now it's a 2 times 8 minus a 14. So trying a little bit harder on the arithmetic, I believe this is a negative 6. So 2 by negative 6 would give us altogether a negative 12. So one last one to go. Some of them are fast, other ones are a little bit more involved using properties of determinants. And the last one, determinant A3B, first goes like this, matching up the pattern in Cramer's rule. The 3 says put B into column B now, so 082 goes here. Then go to the original matrix A, either here or where you took the determinant, copy in the rest, 2, 0, 0, 1, 3, 0. And again, just as fast as before. Thanks to that, or hang on. Oh, I think I made a mistake on this. When I was looking into this determinant of A, I was copying those 2 0 zeros. You know, that looked good. That's the wrong matrix, though. You have to use legitimately this matrix right here. I probably should have wrote in the step A here before I done that row operation, because this is the wrong column altogether. Let's make a switch on this and also fix it on the one below. And that's good word of warning. You have to use the original matrix A. If I do any changes here down to this one, I'm potentially changing the output down below right here, because the row operation I did on this matrix A had to include a different column 2 than what we put in, 082, not 15, negative 1. So we got a number out, but that's not necessarily the right number. Let's backtrack on this. Maybe put in a word of warning on this one. The way I wrote out my work was confusing to me, so I hope it didn't confuse you as well. But maybe it's a good thing that happened. It's a good reminder that right here, we must use the original matrix A. We got 12 below, so let's see how that answer changes. Using the original matrix A means this should have been, oh, hang on. We did the same thing on this one too, didn't we? Oh man, that's rough. Let's fix this one as well. Sorry about that, folks. Well, let's go back to the drawing board on both of these. We got 24 and 12. I'm just going to put this over here just as a reminder. Let's see how off we get when we fix both of these at once. 3 by 3 is not a fun one to screw up on, but it's good to do it right, especially for the sake of learning the pattern here. So going back to the original matrix A, make sure you're looking at this one, nothing that you've computed in the middle like we did over here. Determinant A1B should involve a 1, 5, negative 1, negative 3, 1, and 4. We should probably pause right here. Does that make sense to folks on what the error was and the fix is?
So is that really a problem though? Because like when we do the row operations, we're not actually changing the solutions, right?
That's true if we're just dealing with a row operation in, say, Gaussian or row reduction for solving the solution. But when it comes to the determinant, swapping out a column like this and changing from these to these, I believe it could actually change the determinant itself in that case. Let me think about that question a little bit further. So yeah, if we're solving this system and augmented with 0.82 here, row reduction wouldn't have caused any problems. But if we change one column right here versus this one, which is a, let's see, it's an equivalent system. You know, that's a pretty good question, actually. Yeah, the systems are equivalent, they're row equivalent. The determinants are the same using properties of the determinants in section 3.2. But putting an 0.82 here, the row operation that we would have taken on this one just wasn't conveyed with this 0.82. If we took the same row operation, that column vector would have changed in a different way. I think that's where the problem is for this, but you know what? We've got the answers recorded, so we'll be able to do a double check on that concept. But yeah, that's a really good point to think about. Let's see what happens with this one, and I'll think about that a little bit further on my subconscious, hopefully. So if we take the same operation, or maybe you're doing it a little bit differently, I notice if you just add row 3 to row 1, you get a 0 here, probably even a little bit faster. Let me copy in the first two rows, 851, 2, -1, 4. Now take, oh, hang on, but if you add these together, that's actually not really helpful, right? You eliminate that 0. Probably the better way to go still is either eliminating the 2 or the 8. The 8 is a little bit easier to eliminate. Adding these together to get that 0 isn't helpful because the 2 replaces what we already had going on, that 0. So let me put in 2, -1, 4, multiply row 3 by -4, adding to row 2 is going to give us a 0, -4 plus 5, so a 9, -16 plus 1, so a -15, then 0, 1, -3. So now going down this column, column 1, we'll go positive, negative, positive on the sign chart. So that would give us a +2. Then the reduced matrix is 1, 9, -3, -15. So this is twice. Main diagonal is a -15. Off diagonal is going to be the negative of 27, so +27. So the difference here, hey, that came out the same. So this is altogether 12 by 2, so 24. Starting to look like that your concept was right on this. Even though we did a row reduction, we still came up with the 24 on this one. Yeah, that's kind of crazy in a way. For some reason, I thought that that concept would be false, but I have to think about this a little bit harder, it looks like. Plugging in a 0.82 here, even if we change the matrix in this way, I'm going to give myself a reminder about this and think about it even a little bit more and come back to you with this on next class. So this is my reminder. Using the theorem, let's say using part 1 of the theorem in section 3.2 before writing out A I B, will this change the result, or will this always be the same? So this is the main idea to think about. Is that about the right thought? Okay, so I'm going to do a little bit of homework on this. Looks like it came out right on this one. Makes me suspect that it's actually a true property, and that we kind of freaked out over nothing on this one, changing it from over here. Let's try this out again. I'll use the original matrix just to think about that property one more time. Original matrix was 2, 4, -2. Then -3, 1, 4. Then doing the same kind of determinant, We indicated going down this way before, but that's when we had this result here, 2, 0, 0. You know, if this is a true property, then that's a fantastic property. This is just a big speed up in the whole process with Cramer's rule by simplifying this determinant A as much as possible, getting loads of zeros to start it out. But if we went this way, I think possibly getting zeros up here would be our fast approach on this one. So let me copy a -2, 2, 4. I'm going to multiply row 3 by 2, adding it up to row 2, giving us 0, 4 plus 8, so a 12, 8 plus 1 for a 9. Then take row 3, add it up to row 1, and that's going to give us 0, 2, 1. Then same cofactor expansion, if we go down column 1, we'll have positive, negative, positive. So just the scalar here in that entry, -2, multiplies the determinant, 2, 12, 1, 9. So we get -2, main diagonal is 18, off diagonal is -12. So this becomes -2 times +6 for a -12. Now I'm starting to misremember. Did we get a positive or a -12 before? I think it was a 12, but I erased that in a pretty fast way. I definitely don't want to Control Z that. That's more to think about with this. I got just about the same thing, but opposite value, I believe, after we deleted it and erased. So there's probably more to think about in these kind of ideas. So let me double check my arithmetic too here as well. So I got 18 minus a 12 multiplied by a -2. Okay, yeah, it looks like we're getting a -12 on that. Yeah.
I can just barely see what I erased, but I originally had -12 on.
Oh, gotcha. So that gives us more truth to this. Looks like it was a -12 originally. Thanks for mentioning that. So yeah, that's kind of weird. I felt like we were going to mess this up by changing out the matrix. By using property from 3.2, the very first property with row reduction, unchanged the determinant, also meant huge speed up on this. Of course, we've kind of spinned our wheels by doing that. In view of that, let's leave this one as a 2, 0, 0 and see how it pans out. So 2, 0, 0 here. If this property works out, it just means this is a pretty fast way to do this one, because now it's in a triangular form, just automatically. This would be 2 times 3 times 2, so this would give us a 12 altogether. And I vaguely remember the solution to this one. We're going to divide everything by 6. That value is right, whether we use the original matrix or the slightly reduced one over here. So that might be something you think about taking advantage of when you go to do a 3x3 in the homework. Using this property here looks like it's legitimate, but I'll come back and discuss this when we come back next class to see what I can learn about this. You always worry about, is this a coincidence? Probably not. It's a pretty random looking matrix, or is it a real property that's working? But now to put all of this together, we have 4 components. And this is the big punchline to Cramer's rule. We can say, therefore, this original system, which we have probably solved 10 minutes ago with ordinary row reduction, it has a solution that goes x1 is determinant of a1b, 24, divide by 6, the original determinant of a. So x1 is automatically a 4. Let me just put a little highlighting to show how all those connect. x2, go to determinant a2b, -12, divide this one by 6. We get a -2 on this one. And likewise for the last one, x3, that's going to be +12 divided by 6. So on all the values, we're always dividing by the same determinant, the determinant of the original matrix A. The only thing that changes is these different determinants that we formed by inserting column B into the right positions. Well, that one was kind of a slog. We got through it though. Thanks for the help on getting through this, whether it was the arithmetic or the other ideas. Other questions at the moment on finishing this one? Okay, so that's Kramer's rule. It's a lot of work for a 3x3. Once again, think about the reason we have done this is just for a better understanding of what the actual pattern looks like for Kramer's rule, moving the column vector B across and assembling the solutions in this way. For slightly more legitimate use of this would be situations like these. The author does a little bit of a discussion on the value of doing these kind of problems when it comes to modeling different kinds of things in application problems. Oh, sorry for missing the chat as well. It seems like that works because there was not an actual operation that changed the matrix. For example, no scalar multiplication or anything. Yeah, absolutely. The critical thing there, like Brian was saying, is because we just used the property 1 that says the determinant is totally unchanged, that looks like it's the major thing that was working for us. If we did something different, like interchange the rows, we would have to reflect that new change down below here somehow as well, or just scalar multiply one row and leaving it like that. So for example, this was 1/3, 7/3, 5/3, and we put 175, then that property would break down unless we included that additional fix. Other questions or comments at the moment? Okay, so let's try this out next. One last time on working for when there's a parameter in the system. Looks like a pretty fast problem, really. Only thing we're dealing with here is the new parameter S. And the value for this is, in Kramer's rule, if you had a bigger system, maybe it's of size 20 by 20, 20 equations, 20 unknowns, or really a lot larger, but you're interested in one part of the solution, what the value would be for, like, say, x7. Kramer's rule can isolate just that one single part of the solution and show how that solution changes as the parameter S changes itself. This is our author's big attempt at showing a useful application to Kramer's rule. It's kind of hard to do because, once again, its major purpose is a theoretical tool. But for extra practice, if we're going to solve this using Kramer's rule, we want to first determine when the system has a unique solution. So we would write it out as AX equals B, find the matrix A, the column vector B. To address this part, whether the solution is unique, it's really just another invertible matrix theorem problem. The solution is unique the moment we know A inverse exists. Really can think of it as really theorem 5 from section 2.2. It says that this has a unique solution providing A inverse exists. That's the A inverse part right here. So let's just take a look into A inverse. We're not going to compute it directly, but we're just going to calculate the determinant of A to see if it exists. Pull the scalars, 2s, 3s. Next is going to be scalars 1 and 6s. Take the determinant of that, we'll get 12s squared minus 3s. But the value of this being non-zero or not now depends on the parameter s itself, so we need to work with this a little bit more. Let's factor out a 3s, leaving behind 4s minus 1. So this determinant is not equal to 0, provided s is not 0, and let me fix that 0 there. S is not equal to 1/4, coming from the opposite factor. So we have a non-zero determinant for those two specific values of the parameter S, and this means we can say, therefore, the solution is unique when S is not 0, feels a little bit redundant, but let's say it is to be specific, and S is not 1/4. So we have a unique solution in those cases. Now we'll just describe the solution set by Kramer's rule. We already have one big part. This is the determinant portion. So we just need to look into A1b, A2b to get the total result. Any questions with the first part, just looking into the unique solution portion? Okay, so this is our last run through with Kramer's rule. we have that x1 is determinant a1b divide by determinant of a. We've already calculated determinant of a, so in this portion, we'll put in the 3s times 4s minus 1. In the numerator, determinant of a1b takes a column vector b, which we never really indicated, but that's the 1, 2 right here. So that's supposed to be the eraser. Column vector 1, 2 goes into this position, and the rest of the matrix A, 1 and 6s, goes in their remaining spot. Let me take another look at that S. The challenge with S is to try not to make it look like the number 5. So this next determinant, we get 6s minus 2 divided by 3s times 4s minus 1. So provided s is not 0 or 1, this is how the first part of the solution, x1, would change as you change the parameter s in those 3 different positions. Not much more to do with this one. Factoring the numerator isn't going to reduce it down, so I'd probably just leave it right in that format. But we have one part. This is the x portion. Next is x2. For x2, we do the same kind of thing. Take determinant of now a2b, divide by determinant of a. Make those same substitutions. 3s, 4s minus 1 in the denominator. New determinant we take places 1, 2 into column 2. It takes this from the original determinant, 2s and 3s. And finally, we have from this determinant, 4s minus 3s, divide by 3s, 4s minus 1. This one does simplify a little bit, so we have just s in the numerator, 3s times 4s minus 1. So we have 1 over 3 times 4s minus 1. So that's what would happen with the second solution. Interestingly, once we reduce this down, it doesn't depend on s, but still s cannot be equal to 0, or else we would have a problem with the x1. So there, even though you can get a value here, even when s is 0, it's not a solution any longer because it broke x1 itself. That's another thing that's kind of weird about dealing with parameters. It looks like something's valid here, but you still can't plug 0 on this one either, even though it's defined. This equality is, again, a bit of a lie. It's only true when s is non-zero and not 1/4. We did it, folks. That's just our last look into Cramer's rule, just another way to practice it. Any questions at all finalizing this one? Okay, well, we did it, folks. That's the end of chapter 3. Very computational chapter. The next chapter we're going to look into, chapter 4, is going to be less computational. It'll feel really abstract at first, but once we get into section 4.2, dealing with null spaces, it'll feel a lot like chapter 1 once again. We're going to do similar kind of things that we've done in the past, just give it new definitions and terminologies. Well, the next thing we're taking a look into is essentially this stuff in a certain sense. When we were all the way back in section 1.3, we defined what we meant by a vector once and for all. We did this again in section 2.1, except they were larger objects, they were matrices. But we made a big deal about vector addition and scalar multiplication. We said that this is really the big thing that forms a vector space. But to really say that what a vector space is all at once, you have to go through a number of axioms, and here are what the axioms look like. It's a lot of stuff. So here are the axioms of a vector space. Because this is so much stuff, it's good to have an analogy that goes along with this. And there's a couple of analogies in mathematics. One big analogy is down here, Euclid's axioms. I think just about everyone's come across Euclid's axioms in one shape or form. The idea with Euclid's axioms is Euclid himself did some really foundational work on geometry about 2,325 years ago. he came up with these axioms. It was just 5 undefined things, or excuse me, 5 axioms involving undefined objects. The straight line may be drawn between any 2 points is one of those axioms. We won't go through all of them, but here's the refresher of all 5 axioms. And what was critical about Euclid's work way back in the day was he never defined what he meant about a straight line. He never defined what he meant by a point. So any system that has a notion of line and point and satisfies axioms 1 through 5 can be brought into his geometry. And all of the things he proved in Euclid's axioms, and there was quite a lot, was bona fide mathematical work that researchers do today. This stuff has been investigated a lot. People even reformulate postulate 5, and hundreds of thousands of hours, probably more, of energy trying to show that axiom 5 can be proved through axioms 1 through 4 have been invested. It's always failed. Really, for axiom 5, it had to be a new axiom itself because it's something that couldn't be deduced with axioms 1 through 4. So if you've looked into Euclid's axioms before, might be a nice page to go to as a refresher. We're doing the same kind of thing over here with a vector space. Instead of saying things like points and lines, our objects that we never define exactly are vectors. We'll never say what they are exactly. We have some intuition of what they could be. The section 2.3, or excuse me, and section 1.3, those are vectors. The vectors can be really, really abstract things. They could be a function like sin x that we've hinted at before, or something totally new and arbitrary. So whatever your vectors are, if they satisfy axioms 1 through 10, we have a bona fide vector space. So this is really just the foundation of the theory of vector spaces. It's exactly what we're doing in chapter 1. So chapter 1 is our big example of what a real vector space actually looks like. And just like Euclid's axioms, you can't delete any single one of these. For example, you can't derive axiom 10 using everything above. You really need this right here to get everything to look like it did back in section 1.3 with the vectors in Rn. The major things that we're going to be discussing is the closure properties. These are fundamental since if you have vectors, you also need 2 other additional concepts. A way to add your vectors together, vector addition. The way to multiply your vectors, scalar multiplication. But we have to have a rule that if you're multiplying your vectors, closure means anytime you say, I'm looking at multiplying, anytime you multiply a vector, say c times u, it's still in the vector space V. If that ever fails, we're not looking into a bona fide vector space. So this is how chapter 4 starts. It's pretty abstract. We're talking about vector spaces. Now axiomatically, these are the 10 parts, like the atoms of what a vector space really is. So we'll look into what a vector space looks like in R5, what the zero vector is. A more abstract vector space, well, we'll show that this one isn't actually a vector space at all. It fails a closure property. And other more abstract vector spaces, like the space of continuous functions on a closed set. These are wonderful functions. You can always integrate them. They form a vector space as well. So we're just going to collect a catalog of examples of vector spaces. Then the computational meat in this chapter is going to be about working with subspaces. This is what carries over into section 4.2. So there's a lot to talk about. I don't know that we'll finish these entire set of notes on Thursday. This is not notes you'd really want to rush through. But we're going to make our start when we come back next Thursday, starting back on the top here. But any questions at the moment with just our preview of vector spaces? Okay, well, have a great afternoon, folks. I'll look into this concept again. It looks like it's absolutely true. This was really surprising to me. So thanks for mentioning that. That's a huge speed up again on doing these kind of Cramer rule determinants as well. But otherwise, have a great afternoon, folks, and I'll see you all on Thursday.